Alright guys, so we've already talked about solids, now let's talk about liquids. And again, I'm not going to spend a lot of time on liquids. Liquids are really in this chapter for the purpose of looking at vapor pressure. And that's really the only purpose behind talking about liquids right now. But liquids have low compressibility. Basically that means they cannot be compressed, and that is because the molecules are as close together as they can be. Remember, these are similarly spaced out as a solid would be. The only difference is solids have more intermolecular forces holding them rigid in their position, versus liquids have less intermolecular forces, still a lot of them, but less than a solid, so there is the ability to flow and to move around, but they're still very compact and close together. Okay, and then they also have high densities, and that is in comparison to their fellow gases. So that's about it in terms of liquids, in terms of properties. Okay, let's talk about vapor pressure. So you saw a little bit of vapor pressure in the lab you did for gases, but we haven't really talked too much about it. So let's just kind of get a basic idea. First off, we have the idea that liquids can vaporize and condense. Vaporization means it turns into a gas, and condensation means it's turning into a liquid. Okay, what happens with vapor pressure is we reach equilibrium. So we've already discussed equilibrium. It is when, it is when the two processes, the vaporization and condensation of the liquid, are balanced with each other. It means the rate in which the water is turning into a vapor and the rate in which the vapor is turning into a liquid equal each other. So kind of start out here. We put a little bit of water in a closed container, and note this does have to be a closed container. The minute the container is open, you have the ability for the gas to escape, therefore the gas never builds up over the liquid. Okay, so immediately as soon as you put any liquid, technically, but we're just looking at water here, into a closed container, some of the gas begins to form. It begins to vaporize on top of the liquid. Okay, from there, as the vapor builds up, it's going to start condensing back into its liquid form. And eventually what's going to happen is the amount of water that turns into gas and the amount of gas that turns into water is equal to each other in terms of rate, meaning let's say 2 molecules of water turn into gas at 1 second, therefore 2 molecules of gas turn into liquid during that 1 second time frame as well. So when you put water into a closed container, you're going to notice an immediately decrease in the volume. Actually, you probably won't notice it, but if you could get down onto a microscopic level and actually see what's going on, you would see it. But otherwise, on our scale and the macro scale, we really don't see that drop. But it's going to decrease at first, and then it's going to slowly increase, and then it's going to balance out. And that balance out is still going to be less than where it was originally. Okay. Now again, all substances technically have a vapor pressure. Okay, and again, vapor pressure is the amount of gas or vapor at equilibrium above the liquid. Okay, so vapor pressure, again, what is pressure? Pressure is the amount of collisions. The higher the vapor pressure, that means there are more collisions. That means there's more gas molecules. Well, what would allow there to be more gas molecules above a liquid? Well, that's going to come to the fact that it has weaker intermolecular forces, meaning the molecules are able to escape the liquid phase at a much higher rate, and therefore there's more gas molecules, more collision, higher vapor pressure. Okay, and water's got fairly strong intermolecular forces, so its vapor pressure is actually fairly low. Versus if you go to, let's say, Publix and pick up a thing of rubbing alcohol. A lot of times the rubbing alcohol canisters, when you grab them, they're sealed, and a lot of times they are very, very tight. They're hard almost, and that's because there's so much vapor above the alcohol, above the liquid, because it's got such weak intermolecular forces in comparison. Okay, so the gas is able to escape easier. That's also why if you pour a little bit of rubbing alcohol on a counter, it's going to evaporate much quicker than water would because, again, weaker intermolecular forces, which again goes back to that vapor pressure. Okay, so vapor pressure, here's one of the questions. We actually saw this question, I want to say something similar to this. I think I changed it a little bit back on the intermolecular forces chapter last semester, but let's kind of look at this again. We have 4 substances, C6H6, benzene, C2H5OH, ethanol, CH3OH, methanol, and C2H6O2, which I want to say is a ethanoic acid. Okay, from there we're given vapor pressures of 75 torr, which is the same thing as millimeters mercury. 44 for our ethanol, 92 for our methanol, and then 0.06 for our ethanoic acid. Okay, so just kind of pay attention to these. We have 75, 44, 92, and 0.06. Remember, this is pressure. So these are the amount of collisions, if you want to think about it like that. So the more collisions means there's more pressure, and more collisions means there's more gas particles. Okay, more gas particles means weaker IMS, means more molecules were able to escape the liquid phase and turn into a gas. So, based on the data in the table above, which of the following liquid substances has the weakest intermolecular force? That's going to be the highest vapor pressure, which is going to be the 92 torr here, which means our methanol. Okay, which one would have the strongest intermolecular forces? It'd be this 0.06, due to the fact that this means there's very few collisions, which means very strong intermolecular forces are holding the particles into the liquid phase. So in this case, our answer is looking for weakest, so our answer is going to be C, methanol. Okay, so that's liquids. That's all we really need to do with liquids, and moving on. Okay, from there, we go into phase changes, specifically something called a heating curve. I don't believe this is something we talked about last year at all. So it's something I want to talk about now. What I want you to do, I want you to notice a couple different things. First off, a heating curve is showing the transition of temperature and energy. Energy is here on our x-axis. As we go from a solid, liquid, and gas, keep in mind that an actual heat curve does not look this nice and neat and pretty. They're much messier than this. And the other thing that's important about this is these are being done at a constant pressure, and then heat energy is being added at a constant rate. And what that basically means is, remember, pressure will affect when things melt and boil and all that fun stuff, and that will be something we talk about when we look at phase change diagrams in just a moment as well. So these have to be done at a consistent pressure. Typically, these are done at 1 atm, and the reason being is this is our standard pressure, so it just allows us to be able to do those calculations. Okay, so what I want you to notice here, a couple different things. First off, we have solids down here at the bottom between A and B. C and D is a liquid. E and F is a gas. And then, of course, our flat lines are when we have our phase changes. So B to C is when we're going from a solid to a liquid. And D to E is when we're going from a liquid to a gas. Okay, next thing I want you to kind of notice is, or pay attention to here, is between B and C, technically, a phase change is at equilibrium. And I don't know why I just wrote equilibrium with a G. Okay, so both of these marks, B to C and D to E, are at equilibrium. And what that basically means is the amount of solid turning into liquid and the amount of liquid turning into solid during this state, during this temperature, is at a constant rate until we get beyond that temperature, at which point in time we see a much higher transition, or we see a full transition into all liquid. Same with this up here, liquid to gas. They're going to be transitioning back and forth at equal rates until we get to basically that next temperature, at which point in time they'll transition all to gas. The next thing here is this is a constant temperature all the way across for both of these. Why? What's going on here? Why is temperature not changing? We are adding energy, and keep in mind, time, our x-axis, can also be energy. Kind of depends on what we're doing, because energy is being added at constant rate. You could have either down here, and they mean the same basic thing. Why is a phase change not changing temperature? Why is it occurring at that same temperature? Okay, the reason being is what's going on in a phase change. Okay, and that's when we're breaking our IMFs. Okay, so energy is being added, but what's happening to that energy? That energy is being used. So think back to the fact that kinetic energy is not equivalent, but is proportional to temperature. And of course, energy is kinetic energy. So if we're adding energy, we're basically increasing the energy of the molecules, but we don't see a temperature change here because that energy is being used versus being turned into kinetic energy. So we see a temperature change as we're going from A to B and increasing the amount of energy of the molecules, therefore increasing the kinetic energy, increasing the temperature. But between B and C, that energy that's being added is actually being used up to break the intermolecular forces, resulting in no change of the temperature. Okay, and then from C to D, same idea. We're increasing energy. That energy is going into the kinetic energy of the molecules, making them move faster and speed up. Okay, until we hit part D, which at D, we start having the energy being used to break the intermolecular forces until we get to E, where again, E to F, we're increasing the amount of energy, therefore increasing the motion or kinetic energy of the molecules, and therefore increasing temperature. So that's something we want to pay attention to, is the fact that these are constant temperatures. These temperatures also will correlate with the melting point and freezing points of the substances, or melting point and boiling point. So down here we would have either melting or freezing, depending on which direction you're going, because these can go up or down. And then up here we would have boiling or condensation, again, depending on which direction we're going. Okay, next thing I want you to pay attention to is the length of these horizontal plateaus, if you will. Going from a solid to liquid is fairly short. Going from a liquid to a gas is very, very long. I want you to stop and think, why might that be the case? Why would it take more time or more energy to go from a liquid to a gas than it does to go from a solid to a liquid? Okay, and the reason being comes down to the IMS. Remember, going from a solid to a liquid, we go from having a lot of intermolecular forces to having a little bit less intermolecular forces, but still having a bunch of intermolecular forces. So liquids have a lot of intermolecular forces, but they have a little bit less than a solid does. Think back to the gummy bear and toothpick activity we did last year, if you remember that. Liquids still have a lot of intermolecular forces, just not as many. Versus if we look at a gas, how many intermolecular forces does a gas have? Essentially none, or very, very few and far between. So when we're doing this solid to liquid, we're breaking a few intermolecular forces, but when we're going from a liquid to a gas, we're breaking all or almost all of the intermolecular forces. So there is a difference in amount of energy or time required for those two processes. The other thing you'll see is a lot of times these horizontals are not at the same slope or angle, if you will. And that also comes down to how the substances absorb energy. And that is called specific heat capacity, if you've ever heard of that word. Okay, and we'll talk about that in just a minute as well. Okay, so just some more definitions. So we already know these terms, endothermic and exothermic. Endothermic means it's taking energy in. This is the breaking of our intermolecular forces, requires energy, so endothermic. Exothermic is giving off energy. This is when the bonds are forming, they're going to be releasing energy, and we'll talk a lot more on that giving and taking energy when we talk about thermochem, because this is dealing with both potential and kinetic energy, and is fairly complex, so we'll deal with that a little bit later. Big thing here is to make sure we remember breaking bonds is always endothermic. It always requires energy. So as we're going up this heating curve, it's always going to be endothermic. As we're going down the heating curve, it's always going to be exothermic. Okay? Because we're dealing with these at 1 atm, we have what's called the normal melting point and normal boiling point. That is basically the temperature in which something melts or boils at 1 atm. So for water, when I say what's its melting point, and you tell me 0 degrees Celsius, that's its normal melting point. It doesn't always melt at that temperature. Okay, that depends a lot on the pressure. And then, of course, normal boiling point, same idea. Water boils at 100 degrees Celsius. Again, that's at 1 atm. Not 100% true all the time if pressure is different. Big thing for melting point and boiling point is knowing the definitions of them, or kind of knowing that the definition of specifically boiling point. Boiling point is when the vapor pressure equals the atmospheric pressure. So the fact that here the vapor pressure is equal to 1 atm, that's because our atmospheric pressure is 1 atm. So know the definition of boiling point is when vapor pressure equals atmospheric pressure. Okay, we're going to stop this video here. What we're going to do on the next video is actually work through how to solve the math behind these problems and using this heating curve. Okay, thanks guys.